I'm Kainton, the Tech Pro, and today we are going to take another lesson in our data structures for programmers. And today we are going to be looking at review of AVL trees. As I used to say, these data structures, learning about them is kind of theoretical, kind of boring, kind of not interesting. But as a programmer, you need to have a good theoretical knowledge, a good theoretical foundation on the data structures that actually work behind the scenes in your programs. So that is why I have decided to actually make this. Many might not like it, but I'll say to give you an edge over other programmers, to make you stand out as a professional, you need to learn these things. You actually review them, because I'm sure that maybe in computer science class you've learned something like this years back. So let's now look at AVL trees. Again, AVL tree is invented by Adelson-Velsky and Landis. So that is where the name came from, AVL trees. Now, this is a self-balancing BST. So an AVL tree is a binary search tree. So just keep that in mind. An AVL tree is a binary search tree. And what is the property of a binary search tree? Is that the left child of a node must be less than or equal to the particular node, and the right child of a node must be greater than that very node. So the key thing about AVL tree is that it's self-balancing, meaning that the child of the subtrees must maintain a particular property, that is the height of each child of the height of the two child subtrees of any node differ by at most one. So if this property is violated, a rebalancing or rotation occurs, and that is the focus of this lecture. I want to teach you how to do rotations. So so just keep in mind that we are going to actually focus on doing rotation. So let's examine this tree here. Actually, I'm going to say we have 60. So let me just start here. So assuming we have 60, just a tree with only one node. So here you have a height of 0. Here you have a height of 0. Okay, and it's fine. In this case, here you have a height of 0, and here you have a height of 1, and everything is fine. 0 minus 1 is 1. Now let's assume that we now have, let me take, okay, let's say we have another insertion is done here. Let's say 100. Now this is also an AVL tree. Sorry, this is also a binary search tree, because everything to the right is less than the root. But now let's see, the height of this now is 2, the height of this is 1, the height of the height of this is 0. So we are talking about, and the height of this is 1. So if we take 60, at this point we see that there's been a violation, because the height of the right child of 60 have a height of 2, and the left child have a height of 0. So 2 minus 0 is 2. Is a property of this property has been violated. So now what do? We are going to perform something called rotation. Now this is going to be the simple rotation, but that is actually the way it works even in the more complex one we are going to do after now. What we want to do is a situation whereby we rotate it in such a way that is balanced again. It maintains both the property of AVL binary search tree and also the property of AVL tree. Now what you can think of, if we, let's say, move this 84 up, or maybe move this 60 downwards in this way to the left of 84, then we are going to have a balanced tree, a binary search tree, and also an AVL tree. So what we are going to do, we are going to choose a point at which we are going to rotate. So we are going to rotate it about the child of the node, the child of the node where we have the violation. So we have the violation at 60, and we are going to rotate it about 84. Now what we are going to be performing is right rotation. So let's see. So we are going to be performing a left rotation. So we are going to rotate this 60 have to go down. So in this way we are going to say now 60 has to go down, rotated downwards, and we have 60. Again, 60 has to also be to the left of 84. So here we have 84, and 100 is going to be in the same position relative to 84. So 100. So now we performed a rotation. So normally what I do is to draw an arrow in this way. So I have an arrow going this way and another arrow going this way. So that is the rotation we performed. We did a left rotation. Let's now take a more challenging example. So now let's assume we have, in this case, we have, let's say we have 100, and here we have 60, and here we have 84. Okay, so now let me just write it a bit clearer. 84. Okay, so now if you look at this place, you can figure out that we need to perform maybe more than one rotation. Think of rotating about 60. Now we can actually rotate the 60 in such a way that 100 becomes the right child of 60, right? So we can do it that way. We can also rotate 60 in such a way that 60 becomes the left child of 84. But let's take it step by step. Now what we are going to do here is called a left-right rotation. So the first thing we are going to do a left rotation, and then we are going to do a right rotation. So the first rotation is the rotation we are going to do about 60. If we do a rotation about 60, then we will have a second tree that we still need to rotate again. So let's focus on this part of the tree. Okay, so let's try to rotate about 60, and this time we are rotating, let's say we rotate 6 in this way. So what do we have at this point? So let's see. Okay, let's see. Okay, so 84 goes up. So in this way, let's start by writing. So we have 100 stays in this position, 100 remains in this position. Now 84 goes above 60, meaning that relative to 100, the next thing that now comes should be 84, because we are rotating about 60, and 60 has to go down, 84 goes up. When we have 84 above 60, it means 84 relative to 100 has to be to the left, right? And then we now put 60 back in place. So at this point, this is what we have. So what we just did is a left rotation, and we now have a situation whereby we can perform this rotation we did in the first place. Now we have a violation occurring at the node 100. So here we have a height of 0, here we have a height of 2. 2 minus 0 is 0, and that is a violation. So now we need to choose a point at which to rotate. So we are going to actually rotate this tree about 84, and just like I used to do, I used to put arrows. We are going to rotate this way, and we are going to rotate this way. So now in this case, if we are rotating about 84, it means that 60 relative to 84 have to be in the same I think I drew it wrong, so no, I need to correct this. So this has to be in this way. So basically it's what we already did here. So it means that the position of 60 relative to 84 does not change. So to establish that, we are going to now start by drawing this 84 relative to 60, or 60 relative to 84 does not change. So I'm going to do this. So since we've performed the rotation, the next logical thing to do is to just put 100 in place relative to 84, and the only logical place that we can put 100 is to the right of 84. So now what we actually performed is called a left-right rotation, right? So we did a left rotation and then did a right rotation. There is a place I have the steps that has been followed. So let me just show you the steps that have been followed. So this made this lesson at some point. So this is the procedure for a single left rotation, and this, sorry, what is happening? And this is the procedure for a left-right rotation. So I want you to pause the video, take a good look at it, and make sure you understand exactly how it works. I'm going to stop this so that I'll be able to bring this right in. Alright, so this is about AVL trees. The search time is order of log n, the insert order of log n, delete is order of log n, and the last one I forgot is the space complexity or the space requirement, which actually is a bit different and it takes order of n. And one good thing about AVL tree is that both the search time, insert and delete time, they are order of log n, both in the worst case scenario and average case scenario. So this is an interesting data structure for you to know, have it under your belt. And in the next class we are going to look at, maybe we are looking at split trees or maybe skip list, either of these two. I'd like to thank you for viewing. If this has been informative for you, please leave a comment and also subscribe to my channel if you've not done so before now.